Let's begin part B, if I can get my pen working, of lesson on section 5.4. And it's on the theorem for calculus. We're going to find the total area of the region between the x-axis and the graph of that. Well, here it is on a -4 to 0 position of this cubic. It's a very pretty part, isn't it? So our first step is to find zeros. Find the zeros, we set y equal to 0, and then work out what will make y 0 when x is a value. All right. We're going to factor. I'm going to factor out a 2x. All right. Then I notice that 4 times 2 is 8, and if I add 4 and 2, I get 6 in the middle. So the factors are x equals 0, x equals -4, x equals -2. We'll make those zeros happen. All right, because I need these intervals. This is the positive area, and this guy is the negative area. Right, so we have to break it in two so we can know that area is area. And when we work at it, even though this is negative and this guy is positive, we can then convert that to a positive and make it work. So our next step is to construct the intervals. Well, not intervals, but to construct our integrals to reflect the partitions. Right. So in this case, I would have the integral from -4, and again, we're talking this point here, which is -2, for the function, because we know cap f of x is equal to y, or f of x, of the function. We're adding it because it's the addition rule of integrals, -2, because this will be our negative that we're going to convert to positive. Do the math now. So I'm going to get for the first one, 6x, sorry, I'm taking a derivative and I'm not supposed to. So wrong, so wrong. I'm going to have 2x to the 4th divided by 4 plus 12x cubed divided by 3 plus 16x squared divided by 2. I'm going to clean up this integral. This is from that -4 to 2. And I'm going to clean it up to 0.5 x to the 4th plus 4 x to the 3rd plus 8 x for that position. So this is what I'm going to use for, so here we go. Let me make some room. Okay. So I'm going to have the half x to the 4 plus 4x to the third plus 8x for the position of -4, stopping at -2. And this is the positive side. All right, so we can get it on our calculator so we can do the math quickly. And I took heed when it was mentioned in the classroom. So I have the first one, and then I did the derivative one on line 2. You can see that I have it there, and I didn't cover that. So line 2, the red line, is what we need. So let me go up here, and I can do the -4, then the -2. I should have done the negative first. So at -2, I get 8. I get 0 for the other item, so I have 8 square units for that. Now I'm going to do the same integral from the -2 to 0, so I want 0, which is 0, minus, and then when I do a -2, I get an 8. So I get a -8. So we want the absolute value. So we get 16 square units. There you have it. Again, making accommodations. Well, this one here is very interesting. The reason it's interesting is because we're using an identity of what this position is. So we look on our sheet that everybody should have on common integrals, and an integral that the d of the integral of this guy is going to be sine inverse x. All right, or t, I should say. But before we get to that, let's talk about what happens here. In that calculus theorem, let's look again, way up here. It says that we can have a term in times of t, time, and convert it to x by taking the dx of the whole integral. All right? And what happens here is that the dy dx is equal to the du dx times the dy du. And this part is what is occurring for that x, so that we can change it to x. So I come back down here, and I'm going to say, let u cosine x. And then we're going to say du is equal to negative sine x. All right, so there we have it. When we get to that point and we convert it to x, all right, then we can then insert that. So we know that this guy right here is arc sine of x, or sine inverse of x. All right. So we can state then that when we do this, and I'm going to do sine inverse, we're going to have the sine inverse of x dx by dx, because we're doing dy dx. All right, now that I've done that, I am going to go back and do the conversion that this sine x sine inverse of x. All right, so we're doing it from 0 to pi in that vicinity. Well, these two guys are inverses of each other, so it's a -1. -1. These guys just, the math of it, because they're inverses of each other. Now, this one here gave me problems when I was looking at it because I made it difficult. We know then that y of 8 gives us -7. So this is a limit. And section 5.3, that it's the j. And and here is our dy. So in other words, we're going to make an integral here, because that's what they want, an integral. So we want the integral from our start point to an end point of the function, and then our dx minus that 7, and that's it. All they wanted was to construct it. This is that j that we studied in 5.4. This is our last problem. And this was kind of fun because it gives us the heads up on multiple things that we've learned in the process. And remember, we can get values. We can get time, distance, all kinds of things from the integral if we know the theorem for calculus, besides having the Riemann sum converted into an integral to get area. So in this one, we have two parts. We have temperature in Fahrenheit of a room at T minutes is given by this formula. So we have T equals 85 minus 3 square roots of 25 minus T, where T is time. And we're looking at 0 to 25. All right, so these are the limits, because if we reach 25 minutes, we end up with 85. So the temperature at the beginning is important as well as the temperature at the end. So let's see what we want. We want to find the temperature when T is 0. Well, this would make it 15. So I would have 70 degrees Fahrenheit at the start of this test. The next one is, they want T equals 16. So I've got a 9 on this guy. So I end up with 76 degrees Fahrenheit. Our last point, which is the end, the extreme, is the 25. So we get 85 degrees. So that takes care of that portion. So we have the 85 degrees Fahrenheit, 76, and we started at 70, a very comfortable temperature if it's hot outside. Find the room's average temperature for this point. Well, this is where our integral comes through. And we know that in this case, it's an integral of 1 over b minus a of the integral ab of the function f of x dx. So we're going to do that. So this is going to be 1 over 25 of the integral from 0 to 25 of our function right. So this gives us 1 over 25 of 85t, sorry about that, minus 3 times, and I'm going to change this to 25 minus t to the 1/2, and that's going to make it 25 minus t to the 3/2 times the reciprocal, because we're dividing by it, 2/3. Okay, and we're going to clean that up, and that's from 0 to 25. All right. Oh, and a negative for that part, because we would have to do the chain rule in the other way, so we have to do it on this one as well. So I would have, I'm going to clean it up. This is going to become a plus. Oh, and this is going to be a 2, because this times that. Sorry about that. I don't want to do too many steps and lose you all. From 0 to 25. Okay. So if I put 25 in, because I'm going to now do this part, I'm going to have 0 here. And I'm going to subtract the 0. If I put 0 in there, I'm going to have 2 times 5 raised to the 3/2. I better put 20, 25, because I haven't taken. I did the square root. Okay, because we want to use our calculator. Here we go. And yes, you could do it an easier way, but we have to use what we've learned in this process. So I'm not going to worry about the 25 divided into that. I'm going to just worry about the brackets. So I'm going to have the 85 times the 25 minus the 2 times, in parenthesis, 25 parenthesis of caret parenthesis 3 divided by 2 parenthesis, and I get, let me see if I entered right. Yeah. 1875 divided by the 25. 75 degrees Fahrenheit is the average. Now, the beauty of this problem is the using of the integration of the function that gives us the same degree as if we had done all of it manually to find each of the minutes and then divided by the 25, add them up and then divide by 25. This is the beauty of calculus, and I thank you for listening.